So, hello guys, welcome to workshop number 5. So last week we were going through the OpenRocket basics, and we built a scratch model rocket, like a prototype, and went through the basics of OpenRocket. This week we're actually going to into the complex things about, and there are more, not just designing, but how are we gonna how are we going to build this, and because the final goal is to fly it. So it's going to be mostly Ben who's going to be talking, and yeah, he did design the whole slide, so thanks to Ben. Do you wanna say something?
Yeah, so basically this workshop will be getting more into the nitty-gritty of OpenRocket, and how you will actually get a realistic design that you'd be able to start, designing CAD off and getting ready to 3D print, etc. So if we go to the next slide, this workshop basically, last workshop we sort of did, from a basic, cardboard tube, adding a nose cone, fins, etc. And then we'll start to look at how to get from that design there. That was the actual OpenRocket that I used to design the rocket you see on the right. So we'll start having a look at, how to get from OpenRocket, like the things you need to consider in OpenRocket in order to design the rocket you see on the right. Yep. Yeah, there you go. That one, I believe, off the top of my head, went to about 100 meters.
Yes.
In one of the flights, it had a bit of a parachute malfunction, so hence the damage you may have seen last workshop, but all part of the fun. So basically, yeah, that's the goal of where we want to get to with these workshops. We want to get you building something like that and flying it. So if you go to the next slide, this is what we covered last workshop. You choose your body tube, you have your motor, you design, fins and nose cone, and you adjust the timing of your, you make sure that you're getting to apogee at the right time for parachute ejection with your selection of motor, etc.
Just basic stuff.
Yeah, the sort of basics. And then next slide is a bit more of the realities of what you have to actually design into your rocket. So I'll quickly run through, what you're looking at here, all the different things you have to consider. So yeah, you have to consider how your rocket is actually going to be joined together. That's the couplers. You can see basically it's, a smaller diameter that slides into the body tube. So in my example, I had one coupler joining the nose cone to the body tube on the left-hand side there. So that's the sort of red rectangle on the left. That centers the nose cone into the body tube and slides it in. And then another one on the right, which centers and secures the fin sort of assembly that's fully 3D printed. You have to consider a very important lesson that I learned the hard way, a motor block. Basically, you have to stop the motor from getting pushed up inside your rocket. Seems obvious, but definitely something you have to pay attention to in your design, and also making sure that it's strong enough to withstand the forces that your motor is going to be exerting, both during flight and when the ejection charge fires, which is, a small explosion of black powder. You have to consider how your parachute is going to be connected to your nose cone and the rest of the rocket, because generally the nose cone will pop off when the ejection charge fires, the parachute will come out, and then the parachute will have to carry all parts of the rocket safely down to Earth. So usually those are all the parts of the rocket are connected to the parachute via shock cord, which are those sort of elongated, dotted gray boxes with the zigzag inside them in the model. But yeah, basically you have to be connected everywhere. You have to consider launch lugs. So basically, how is your rocket actually going to connect to the launch tower? In some cases, you'll have like a metal rail with a slot in it that your rocket's launch lugs will slide into. And in other cases, you'll have a launch rod, which, you'll have a long, straight, skinny pole that you will have like a piece of large straw is a good choice sometimes to have on the side of your rocket, and that'll slide over the pole. So if we go to the next slide.
So this is the model. Yeah, go ahead.
Yeah. So I'll run you through some general steps for, designing a model rocket. Some of this will be, running over ground we've already tread, but, just, making sure that this is all clear and making sure you have these slides to refer back to. So with our motors, we're getting C6. I believe we have some C67s. Is that correct, Kaz?
Yeah, have a look, everyone.
Ooh.
You can see me. You. There we are. We got 6 of them for now, but we can get more later.
So yeah, so we have some C67s. So you can tell by the late ejection time that you'll want to be going nice and fast and high. So that'll be good fun. But anyway, back to it. Was that sorry? Did someone ask a question or something?
I don't think
someone said that's good, which is
it is good. All right. So sorry, can we go back to step 1, Hasan?
Yep.
So yes, when you're getting a rough idea of how big your rocket should be, you look at the motors you have available and you try to figure out how much weight would this motor actually be able to safely propel. So we do that with a thrust to weight ratio, where we look at our thrust that the motor is providing and compare that to the weight of the rocket we want. Crucially, this weight is going to be in newtons, so we multiply the weight in kilos by gravity to get the force due to gravity on an object, which is also called its weight. Basically, you want a thrust to weight ratio of at least 4:1 for your rocket to fly stably. Generally, people recommend around 8 or 7 or 8 sort of thing for a very it's going to be stable. 4 is sort of the minimum that I've found. So in our case, so that would mean a maximum gross liftoff weight of 150 grams for our rocket on a C6 motor. This is because you have a C6, meaning that it's a total impulse C class and it's outputting an average of 6 newtons per second of thrust. That's the 6. So you put that into the formulas, you get 150 grams is sort of the maximum weight you're looking for.
The 5 minutes like the waiting time, right? Like C65 or C67.
Yes, correct. And yeah, again, for the motor designation, so in a C65, C is basically how much total power it has. That's the class of motor. That's the total impulse, the total amount of potential energy that motor has available. 6 is, the number after the letter is the average thrust. So, how much power the motor is putting out per second. And then the number after the dash is the timing until the delay before the parachute ejection charge is triggered. So yeah.
So technically for this step, you just have to grab anything that handy. So
yeah, basically.
So a cardboard could work, or just like a wrap.
Yep. So this link there is just a cool little thing I found where someone actually made a model rocket completely out of just manila folders and duct tape. Legitimately. Yeah. So just, basically strong card and duct tape. They made the fins, the nose cone, everything just out of that. And yeah, they made a functioning model rocket. So this slide sort of just to show that you don't need you don't actually need fancy 3D printers and exactly sized cardboard tubes, etc. You can get creative, and you can, as long as you follow like the basic principles of making sure that your rocket is stable, having the center of gravity in front of the center of pressure, all that kind of thing. As long as you have that, sky's the limit. So, next slide, please.
Yeah.
So this is what we sort of did last week. The general steps would be you find a body tube that's roughly the right size. This is sort of informed a bit by the weight that we calculated before. Like, if we have a maximum of 150 grams, you're not going to want a 170 gram body tube. You'd probably want to look at something around 50, 70 grams to leave you plenty of room for adding nose cones, etc. So you use the body tube that you have on hand. The 3D printed walls, you'll generally want to start with 1.2 millimeter thick plastic. So that's equivalent to 3 widths of a nozzle. So three walls thick 3D printed PLA is generally strong enough for the purpose. You can, in OpenRocket, you can set the material of your nose cone to PVC. I assume, so can we get like a thumbs up or something if people are familiar enough with OpenRocket, they've played around with it. They know, back of their hand how to change part materials, that kind of stuff of different components. Cool, I can see Cody, Maxwell, Laura, all over it, too easy. And yeah, if you want a refresher on that, there's last week's workshop as well, just going over the general how to actually use OpenRocket. So yeah, for a parachute, there's a really easy way to make a parachute, which is using a bin bag, a large garbage bag. There's videos you can find online where, yeah, basically you just fold it into triangles, cut it at a certain angle, and then unfurl it, and that'll get you a rough circle, and then you just tape string to the ends of it. You get yourself a parachute. From ones I've made, you'll get a parachute roughly weighing 20 grams, and it'll pack down to roughly 15 centimeters when folded in half. So you'll add that into your design. The OpenRocket design you can see there is actually built around a C67 motor, so one of the ones we have. So you might notice, so this is a C6, and if you can skip a couple of slides back actually, Hasan, to the other OpenRocket design I had.
That one, right?
Yep, so you can see both of these designs are actually using a C6 motor. And you'll notice this one is a bit of a chunkier boy than the rocket in the other slide. That's because this rocket here is designed around a C6.3 or C6.5 motor. So basically it can, go lower and slower so that it reaches, so basically it's heavier. It'll reach its apogee in, a shorter time. And so it's, suited for ejection being, roughly 3 to 5 seconds, depends on which motor I used, after launch. Whereas this one, we want the rocket to be going up for 7 seconds after the motor cuts off instead of 3 seconds. So it's, designed to go higher and faster. It's a much slimmer design, a minimum diameter rocket, they call this one, because it's, just bigger than the motor that it's using. And this would be sort of ideal for, a C67 motor. And it would go to, this one would be going up to 450 meters. So good fun.
Just building a rocket out of kitchen stuff.
Yeah. So this is a rough checklist of what you actually want to, make sure that your design has in OpenRocket. So we'll run through the checklist, and I'll be asking people, what actual simulation option would be best for checking this criteria. So an easy one to start off with how do we check the timing of our motor ejection? We want it to be at most 2 seconds after apogee. What are we thinking? Chuck it in chat if you don't want to speak up. So to be clear, of the options in OpenRocket for simulation on the right-hand side, which of those would be best for checking, when the which would be best for checking what time after apogee there we are. So yeah, you'd look at the vertical motion over time graph, and that would show you the apogee, and that would show you the ejection charge, and that would
Okay, that's what you mean.
Yeah. So that would be the best way to check the overall trajectory of your flight and make sure that your motor is ejecting at the right time and not either ejecting too early and then your rocket is still moving when your parachute ejects and it gets pulled apart, or too late and it crashes into the ground. Not things you want. So second one, stability over time. This is a hard one. This is where we really need to thank you. So this is, it's very important to be aware of the stability of your rocket as it's leaving the rod. So if you use the stability over time graph, you'll see right at the start, it's often a lot lower because your rocket is moving a lot slower. So because stability is related to the speed your rocket is going, you want your rocket to be going as fast as possible, as soon as possible, to be getting off that rod stably and making sure it's going up straight. Little bit of a trick question. I don't know if anyone's played around enough to see this one, but there's a velocity at deployment value. And that is basically telling us how fast the rocket is going when the parachute is ejected. Hasan, would you be able to actually boot up OpenRocket for this one, just to give people a bit of a look? Would that be all right?
Hasan's muted.
Oh, rip.
Oh, sorry, I didn't notice that. So I'm getting OpenRocket started. Just a second.
So yeah, while you sort of boot that up, basically there is, a value that is telling you the velocity of your rocket when the parachute is deploying. This is something you do need to keep an eye on, because if your rocket is moving too fast, and there can be a few reasons for that, but anyway, if it's moving too fast when the parachute deploys, then it'll be like sticking your hand out the window, holding a parachute while you're going, for example, 70 kilometers an hour down a freeway, right? It's not going to end well. Parachute's going to get torn out of your hand, or in this case, out of the rocket, and you're not going to be happy. So
almost there.
for that one, you would be able to look at actually the total motion versus time graph, if you wanted a bit of an idea of the lead up to it and what sort of is actually happening. Because the total motion versus time will be able to show you that if your rocket, for example, has started to, veer off horizontally a bit, and if it starts flying horizontally, which can happen if it is overcorrecting and flying into the wind, that's called weathercocking. Then your rocket can be moving sideways too fast to safely deploy the parachute. And for all of these criteria, you always want to check it for a wide range of wind speeds. So your rocket is going to behave very differently in 2 meters per second wind, which is, roughly 7 k's an hour, like a light breeze, versus, up to 6 meters per second, which would be about 20 kilometers an hour, which would be a bit more gusty, that'd be a reasonably windy day. Not gale force winds. This is like pretty common weather, so it is definitely something you have to be prepared for. If you look up if you look up the weather, it'll tell you, 20 to 25 to 30 sort of kilometer an hour winds is pretty frequent. So anyway, you do need to make sure that your rocket is able to fly in different weather conditions. So yeah, if you full screen that and show us the so in the flight simulations tab.
Just a second. Is the zoom tab that's in the top?
Yep.
Let me move it. Yep. So new simulation. Is everything all right? Yeah.
Yep. So if you just close, so yeah, we'll see that. So to be clear, that menu on the slides that I had, see the menu that says vertical motion versus time. Can you click on that? Top middle of that window. You're just up one there. So if you click on that, so these are all the different options that you can see, and that'll let you analyze different aspects. So if you, for example, give us an example of the stability versus time, please. And if you click in the top left corner and drag, so of the graph, if you click, oops,
Oh, wait. Yep.
to zoom in, you drag a box over those squiggly lines starting in the top left.
How do you zoom in? Is it better?
No. So you, yep. And to sort of like basically you like box select, right? So click and drag. Yep, just that. Beautiful. All right, so we can see Hasan has built a beautifully stable rocket. It starts off on the left-hand side. When it clears the rod, the red line there shows its stability, and that's 1.3. That's above 1, which is what we want. That is great. That is beautiful. So Hasan's rocket is, going to not spiral out of control as soon as it leaves the rod, which is a good thing. So, now, thank you, Hasan. If you could close that and just look at if you close that as well, and see those simulations 1 through 5 that you have there, you can see the 1, 2, 3, 4th statistic in the 4th row.
The fourth one?
The 4th column, my mistake.
Oh yeah, sorry.
You can see there, it says velocity at deployment.
Yeah.
And so because Hasan has timed the ejection of his motor to be near apogee, it's a very low velocity at deployment, so he's not going to have any problems there. So basically, that is where you check your velocity at deployment. If you could look back to the slides quickly, please, Hasan. Another thing you have to check is the altitude your rocket will reach and how far it's going to drift away. So, this is important because you don't want to go losing your rocket over people's fences. All right, for this one, I will take some guesses. Anyone familiar enough with OpenRocket to tell me which would be the best way to check how far your rocket will drift under parachute? Can people draw on the slides, actually? Or just host?
I was going to say, oh, okay, you go.
Sorry, you go ahead.
Okay, I was going to say you could either do the ground track or you could do the flight side profile.
Perfect. Both answers are correct. Loves it. Thanks, Cody. Yeah, so you can either look at the side profile of your flight, which will give you an idea. That's also good for giving you an idea of how far your rocket might be weathercocking. So if your rocket is veering off to the side heavily in your flight side profile, it might be veering into the wind, and that's something to keep an eye on. And then ground track will just give you an overall view of how far your rocket will drift. So we'll give that a shot if you don't mind, Hasan.
Yep.
If you could go back to your OpenRocket design and just choose a sim and give us a flight side profile to start off with.
I'll just run a new simulation.
Yeah, beautiful. All right. So we can see here that on the right-hand side, the little explodey icon is ignition. The rocket is going up for about 100 meters under power. That little puff icon is when the motor burns out and stops firing. And then the ejection delay begins from there. So for the next, which motor are you using actually, Hasan? Is that a
C65? Yeah.
So for the next 5 seconds, the rocket is, continuing under its own inertia. You can see it sort of veering up a little bit, but, that's over 150 meters. It veers off 20 meters, 25 meters to the side. So weathercocking, yeah, not too bad. And then we can see this is in low winds, remember. This is for 2 meters per second winds. You can see when the parachute deploys, obviously the rocket isn't falling very fast, it's just drifting, and it'll drift 85, it'll be pushed by the wind back 100 meters with a net result of being 85 meters away from the launch site. So this is something you always need to look at when you're thinking where to launch. If you're wanting to launch in your backyard, this is probably not the rocket for it. Don't want to lose it over your fourth neighbor's fence.
Yep.
And just to give us an example of how wind can affect this, Hasan, would you mind going back to the edit in the bottom left of that window there? Yeah, edit. And bumping up the wind speed to 6 meters per second. No, that's the wind direction.
Oh, sorry, my bad.
All good. Sorry to put you on the spot here. I would have been doing this if I didn't have to use my phone. So yeah, bump that up to 6. Flight side profile, view. All right, so you can see there that the obviously the rocket has corrected into the wind a bit more. So it's going for the 200, so its apogee is lower, you might note. Before it reached 250 meters high, and now it's reaching 230 meters high. So basically, because it's spending more time going sideways, it's spending less time going up, because it's going 50 meters across by veering into the wind a bit. And then parachute deploys, starts to drift, gets taken by the wind, and gets blown 300 meters away from the launch site. So yeah, again, something to consider when you are launching on a bit of a windy day. You might want to, look at either weighing your rocket down a little, even using a smaller motor, that kind of thing. Or of course, setting up your rocket so that it's like on the for example, if you were launching on a football oval and the wind was blowing towards the west, then you'd set up on the far east side of the oval so that you have as much space as possible for your rocket to get blown away. So yeah, important thing to check. And then just so we can see it, Hasan, can you give us a ground track view? Yep. So this shows you, the overall, gives you, the altitude on one plot and the ground track on the other plot. So very similar, tells you about the same information, but if you were getting, sort of, winds that were sort of not perpendicular or whatever, if you're doing anything super fancy, this might be useful. So yeah, and then back to the slides if you would be so kind. And then of course we have to check that the speed which our rocket hits the ground is safe. If you're going too fast when you hit the ground, that's generally not a good thing. If we can just show people where to find that on OpenRocket, Hasan. It's in a similar place to where the velocity at deployment was, in that just list of numbers in the main simulation thing. So top of your screen, so close that window that you have open, the edit simulation window.
Yep.
And you can see it just there on the right-hand side, the ground hit velocity. Yep.
Oh, yeah, sorry, my bad. Thank you.
And So yeah, that's something to keep an eye on. So you're going to be hitting the ground at roughly, it'd be about 14 k's an hour, I'd guess. I think. Does my math check out? Hopefully. So hitting the
Yep.
ground nice and gently, Hasan. Beautiful. Yeah, and of course you can see, a few of these other numbers are useful as well. Of course, you can just at a glance see the apogee, velocity of deployment. Optimum delay is good if that lines up with, the class of motor you're using, which it does with Hasan's. It says it literally within 100th of a second. Beautiful. It's good. You can see, how fast your rocket's going to be going, how much its max acceleration is going to be, etc. So that's roughly it for the general sort of checklist you want to check off. Next, we'll go into a little bit of how you would troubleshoot and fix anything if these criteria are not being met. So if your motor is ejecting, more than 2 seconds after, apogee, this wouldn't matter as much with sort of high altitude launches, but with, park launches, when you only have, say 4 seconds between your rocket being at apogee and it hitting the ground, 2 second, a second or two of difference matters a lot. So I think we sort of roughly saw this example last workshop when we had the basic rocket that Cass and Anne were mocking up, and then we saw that, okay, the parachute was ejecting too late, so the rocket needs to be going up for longer. So therefore we had to make the rocket smaller so that its surface area was decreased, so that its drag was decreased, and yeah, we fixed that issue. So I'm not going to go through everything on this slide. This is more of a reference for, a general troubleshooting guide, what to do if your rocket is, not reaching everything not doing everything it needs to do. So next, I believe I have a little bit of a walk down memory lane for me. If you could get to the next slide, please, Hasan. So this is a little bit of a sample of all the rockets that I've launched, basically. So starting on the left, this is my first ever design. Not gonna lie, it's a really bad design. Like, those fins are, yeah, about half the size they should be. I think it had a stability of something like 0.4 stability calibers. Yeah, I only, basically this was when I was just learning. I hadn't, done many OpenRocket tutorials online or anything like, I hadn't looked up YouTube videos, anything like that. I sort of had learnt CAD and a little bit of OpenRocket, and I just went for it, and it was good fun, honestly. It was a good learning experience. So that was my first ever design. It sort of spiraled out of control as soon as it left the launch rod because I hadn't checked the stability over time. And so yeah, from that rocket, I learned that, okay, you need to have proper stability. So in the second rocket from the left, the one with the little pink straw on it, the gray rocket, I basically doubled the area of the fins, which moved the center of pressure back to make it more stable. And you can see on the nose there is actually a wad of duct tape that I wrapped around the nose to weigh the nose down, to move the center of gravity forward. And that was something I did on the day just because I wanted it to be even more stable. And that actually flew really well. That was flying, I think, on like an A motor. But that, yeah, went well far. The third from the left is a bigger motor that bigger rocket that I fully 3D printed. So yeah, nice big fins. This one was very nice and stable. The one problem that I had with it is I relied on the friction of the motor sliding into the body tube, I relied on that friction to stop the motor from being pushed up inside the rocket. That friction was not enough, and when I launched it, the motor actually got rammed right up all the way to the nose and was spitting fire through the entire length of the plastic body tube. It did still fly. It was quite an impressive flight, actually, went over 200 meters. But from that, I learned that, yes, you do need a motor block to make sure that your motor doesn't get rammed up inside your rocket. Top right-hand
What
corner,
motor did you use?
that was a B6, actually, I believe. So, yeah, actually about half the power of the B motors we'll be using. But this was a very lightweight design, and it was minimum diameter as well. Like, it was only just as big as the motor it was using. So that, like the OpenRocket design I showed before, if you remember the minimum diameter one, if you could actually just quickly slide back to that.
The troubleshooting one.
No, the OpenRocket design that had, you know, the photo of the OpenRocket design. Two forward, I think. Not that, this one. So this was a similar design in that it was very slim, so it had very low drag, and, you know, a good sized motor. And yeah, that flew. So the B, well, there you go. The B class, it was a similar size to this rocket. And with a B6, the rocket flew to about 200 meters. You can see this one is flying to a bit over 400 meters because it's flying on a C motor, which has, you know, every letter of the alphabet is twice as powerful in terms of, you know, rocket motor classes. So a B is twice as powerful as an A C is twice as powerful as a B, and so on and so forth. And you can see the math roughly checks out. This one is a C motor, and it's flying to 400. The one I flew was a B motor, and it flew to roughly 200. So that was good fun. Yeah, if you could go back to the little slideshow. And so for that gray one in the middle there, I also learned that if you can see the little nub on the left-hand side there sticking off it, I tried to design the launch launch lug into the actual 3D printed design, and it turns out that it's better to just stick a bit of straw, like drinking straw, chopped. If you're doing a very small rocket, it's better just super glue something onto the side. Just makes things easier. You can see the little length of plastic drinking straw, the pink one on the second from the left. That worked out really well, actually. Top right was a actual quarter scale model of our competition rocket at the time. Our design's changed since then, but that's what it was originally going to look like. I flew that once with perfect success. And then when we tried to fly it again, of course it was with an audience when I tried to fly it. It failed miserably because the 3D printed body tube had actually warped from the heat of the ejection charge. So you can see the second, on the right-hand side, the middle photo there is where I actually replaced the bottom half of that rocket with another design I had lying around to sort of fix the warp, and that actually worked out well. So rocket surgery, and that was out in the field with a few people from Aries, and yeah, that actually worked out pretty well. And then yeah, on the bottom right, you have my sort of latest design from last year. So basically, I'm just taking you through that to give you a bit of an idea of, you know, this was over the span of, yeah, roughly a year that I sort of went from absolutely horrible on the left-hand side, but still fun, to, you know, something actually pretty workable on the bottom right-hand side. And so, yeah, that's just a very rough overview of just the basics of starting to, starting to design a rocket and making sure that you get that checklist ticked off, that it satisfies all those criteria in OpenRocket, which, you know, probably telling you some of you have made very good progress in that, and that's really good to see. So yeah, making sure that it satisfies all those criteria, making sure that it's going to fly safely. So yeah, this is a little bit about week 7. If you want to talk about that, Kasanan and Hasan.
Oh yeah, so there won't be any workshop next week. So like a lot of people will have like doing assignments and oh wait, next week is holiday, right?
In fact, there won't be another workshop for the next 2 weeks.
Yeah.
Oh yes, fair enough.
Yeah.
My bad. Yep. So we'll see you in week 7, and we'll be like going through LaTeX. So just to say, it's not pronounced latex; it's LaTeX. And like this is like a markup sort of language. So if anyone has ever used like HTML, it's kind of similar, but a bit different. And so why are we going to use it? We're going to use it to like make our documents. So particularly if you're in right now the project areas, we'll be writing most of our documents using LaTeX. And it's a good collaborative platform. And like you can also like use version control. So you can always like head back to like previous versions. And yep, so that's where we'll get to next week.
I've wondered how all your, basically every single assignment you've ever seen has almost guaranteed been written in LaTeX. It's how they get them so clean looking. It's how they get actual mathematical expressions into the paper without having to mess around with weird word art or whatever. And
there's one other thing I wanna add. So with LaTeX, like for us, for particularly me, I don't actually know how to reference anything. In LaTeX, there's just one command, and it'll refer.
Right.
Yeah. So even you can mention what style of referencing do you want. It'll do everything for you. Yeah. So
Yep,
Cass
so-
and do you wanna add something?
Yes, just I'll quickly mention that there's a launch opportunity on the 10th of April. So what we might do is set up some sort of poll to see how many people are interested in going by the 10th of April and seeing how many people would be ready by then. And keep an eye on the Slack for info on that. Otherwise, we'll try and set another deadline for people to complete their rockets.
Yeah, it's pretty much every month they're launching out of Druin, and every month, but sort of alternated by half a month, spaced by half a month, they're launching up near Bendigo as well. So obviously Druin's a bit of an easier option, but every month at least you'll be able to have an opportunity to launch. And even if you're not launching, do come down. Like, it is awesome to see these old blokes with their like big 2-meter rockets that are going to 1 kilometer and launching them. And last time I went, one of them let me sort of help put together the motor for the rocket, get a bit of hands-on experience. It's just a great experience, no matter if you're launching or just watching. So would highly recommend.